1 is accepted. Now I won't bother with 0011. It's much the same. You've got, I think you've got the idea now. Okay, but a lot of details, right? So maybe practice it yourself, going through the details. Okay, now next example. It's going to be quite a long session, I think. Here's you're to construct a PDA. Find its transition diagram, for example, and well, you can make a formal definition. Usually that involves just a bunch of rules, but from the rules, the transition rules, the state transition, state diagram or state transition diagram. From the rules, you can deduce what the state diagram is, state transition diagram is. Okay, here's the language you are to detect, to recognize using PDA, and it's of this form. So you've got the input string alphabet ABC augmented with epsilon, and you've got the stack alphabet, I assume, is what? Maybe just $. No, maybe that can't be right. No, you're putting these. No, it must. So the stack alphabet must be ABC and epsilon. Right. Okay. So you're to detect. You're to what's the word? Recognize this language. I, J, and K are non-negative integers. Okay, and you've got an extra condition that this integer here, I, is equal to K, or I, so I is equal to J, or I equals K. Right? Now the problem is, now we started talking about this the previous session, and the first thing we did was okay, put all the A's on the stack. Just push. So have a loop that just pushes all the A's, and the first time you get a non-A, then check if the number of A's equals the number of B's, or check if the number of A's equals the number of C's. Now the trouble is you don't know ahead of time whether you're going to get, after your first A's, you'll get a B or a C. Well, after each time you've after each time you've read an A on the input string and you've pushed it onto the stack, for the next step, jump non-deterministically, with all, like here, with all epsilons, all three of them. I don't think Sipser spelled that out too clearly, but my interpretation, when this happens, when all three of them are epsilons, then that's when you make a non-deterministic copy. Right? You make a copy of your PDA, and one copy will go down one branch of the state transition history, if you like, and another copy will go down another branch. And we talked about state histories in an NDA in the past. Well, you'll have something similar here for a non-deterministic PDA. Okay, so what happens here and here? Now you can see the label here and the transition arrow here and here. They're the same. And they're all three of them, the A, comma, B, arrow, C, form of the labels here, like this. they're all epsilons. And when that happens, that's when you make, you split, a non-deterministic split, okay? And so you'll have, and you make a copy of the PDA, and you'll put one copy in state Q3 and the other copy in state Q5. And then these two PDAs from then on just independently process away. They just function independent of each other, okay? And unless they die, they could die. Branches in a non-deterministic tree, if you like, the history of the state changes, state transitions. That tree, you can have branches that die, okay? When there's no further state transition possible, it just dies. That branch dies. So, right. So let's see what's going on here. So you have a look. Here's a broad strategy again. If it starts, you push as many A's as you can until you get either a B or a C. When you get a B or a C, that's when. Is that true? No, you do it. If you look, details, right? If you look at this, well, let's do it here. So it's, this is the actual solution. So it's less likely for me to make errors. Just guessing it myself. But all right. Okay. So should that be an accept state? Let me check. Shouldn't that be an accept state? That's not possible, is it? Hold on. No. In the textbook, it is not an accept state. Okay. So as usual, you push the dollar. Okay. So you know when the stack is empty. So that's old hat now. So you transition to Q2. And what do you do then? Well, you have three choices. Well, two broad choices in a set. One is you read to see if there's an A on the input string. Right? If there is an A, you don't do anything here with the stack. You don't read it. You don't read pop. Okay. And you make the transition, so you go back to Q2, and you push what you read onto the stack. Okay? So you may loop through. So say the input string is a whole series of ones. So you just keep looping through this going back to Q2, and each time you loop, you're pushing an A onto the stack. So if you loop through n times, there'll be n of these A symbols on the stack. But at each step, and that's one possibility. Now another is that you split. You make a copy. So now you have two PDAs. One will be put into state Q3 and the other one into state Q5. So let me try and, in terms of the tree, the history, the state history diagram, what would that look like? Well, so I've got three fingers. So that branch, that would corresponding to looping this way, right? This one here. And then these two would correspond to that one and that one. So you've got, so you have a PDA, and that's at that level, that step level in time going down. Okay, so you get here, and then at the next step, so you go from here to here. That's one step, let's say. So now your stack has $1 on it, and that's it. And then at the next step, time, you'll now have three branches. That one, that one, that one. You have 3 machines, 3 PDAs, one in state Q2, another in state Q3, another one in state Q5. Right? And then the next step, so the state Q3 and state Q5, they do their separate thing. Remember, these 3 now are just functioning independently. But this one, at the next step, it too will split 3 ways. So this outer one, in a sense, each time splitting 3 ways. Okay, it gets quite complicated. But it's all implicit in this state diagram, state transition diagram. Okay, so now eventually, say there are no more A's. You run out of A's. Well, then you can't loop this way anymore.